Hello and welcome to this lecture series on microprocessor and microcontroller. And Currently we are studying 8085 microprocessor. And we are now in the video number 6. And the topic of today happens to be pin diagram. That is, we are going to see the IC diagram as well as the functional diagram of 8085 microprocessor. And we are also going to see some related circuits because as I told you earlier that this 8085 microprocessor itself is like the brain of any organism. So brain alone cannot function. It needs its peripherals to perform certain work, right? So on that note, we are going to see first of all how does the microprocessor looks like by viewing its pin diagram. And pin diagram, we will see two formats of it. One is the IC diagram, that is the integrated circuit diagram, and then there is functional pin diagram. So that's what we are going to see. The difference between IC diagram and functional diagram is that in IC diagram you will see the actual IC. I mean, it is a 40 pin IC, so you will see what is the function of each and every pin. But functional pin diagram simply means that you will see the pin diagram, but then the pins with similar functionality will be grouped together, and that does not correspond to the actual IC diagram, but that gives you the set of pins which have the same functionality. So for remembering purposes, that functional pin diagram is easier to remember. And we are going to see the related circuits. Like we are going to see the related circuit for address latch enable. We are going to see the related circuits for decoding of read-write controls, etc. So that is the topic of today. But before beginning, let us see what we have covered up till now. So, as per the plan, we are now in the sixth lecture, and in the first five lectures, we have first covered the introductory lecture. Then, in the second lecture, we have seen the programming model. And the programming model of 8085 is a way by which the programmer interacts with that 8085 microprocessor without knowing about the internal details of this microprocessor, right? So then we also started some simple programs in that lecture itself, and then we wrote simple programs in further two lectures where we saw how to deal with various parts of microprocessors. So we see how to deal with registers. We saw that how to deal with externally interfaced memory. We saw how to deal with stack, and we saw various operations there. Still, we haven't completed the programming, but it was good to begin with because as I told you that it gives you a good idea when you study the architecture for the first time. So if you're already aware of some basic concepts of programming of 8085 in assembly language, that will help you understand the architecture better, right? So in the last lecture, we were studying the architecture of this 8085, and let me again show you that slide where we studied the architecture of 8085. This was the complete architecture, and we studied this complete architecture. We gave a small introduction to every uh, portion of this complete diagram, and we saw that this instruction register and instruction decoder and machine cycle encoding plus this timing and control circuit is actually responsible for making this complete circuit multifunctional. I mean, the same digital circuit that you have made could perform any desired function because of these specialized components. And this instruction decoder and machine cycle encoding circuit, it actually contains a kind of truth table of the PDF that I have given you. In the PDF, you had mnemonics, its opcode, its hexadecimal code, and its decimal code. So whenever an instruction is read from the external memory through the data bus and address lines, so that instruction is directly put through the instruction register into this instruction decoder. So the instruction decoder, it clearly knows that if a hexadecimal equivalent this much comes, then what does it mean? So this instruction decoder is actually a kind of lookup table where all of the 74 instructions and their 246 permutations and combinations, they are known to it. So accordingly it will instruct the timing and control unit to set the micro operations needed to do that complete task. So this is a very important portion, and this was a major breakthrough at that time because from hardwired circuits we actually started to have the same hardwired circuit perform multiple functions, to perform multiple digital logic functions, and that was a major breakthrough. So that's how these circuits, they were supposed to have some brain in itself. That is, they are able to make permutations and combinations of already stored instructions in this instruction decoder and achieve a certain task. So that's what we meant by programming. A user will make permutation and combination of all the 246 patterns that were there, which were available to him as programmer, and those patterns in a particular sequence which achieves some task is called as a program. So that program is read one byte by byte to this instruction register, because this is of 8 bits, and that's how this complete digital circuit became multifunctional. So that's what we have seen about this architecture. We gave small introduction to every small unit of this complete architecture, and in today's lecture now we are going to see the pin diagram of this and the IC diagram of this. So let me bring that pin diagram and IC diagram here. So first of all, let's have a look at the IC. How does the IC of this 8085 looks? So you can see here that here 8085A is written. So this 8085A, it's a variant of 8085. The initial variant is 8085A. So it hardly matters. I mean 8085, it is all the same. So the thing that we are studying is 8085A, and this is how the IC looks. It looks like any other IC that you will see in your digital electronics laboratory, or you might have seen in your digital electronics laboratory, right? So if you count it, on one side it has got 20 pins, and similarly on the other side it has got 20 other pins. So total of 40 pins are there. A total of 40 pins are there, and you actually know how to do the numbering of an IC. This notch that you see here is helpful in numbering the IC. And how is numbering done? So let me show you this another slide. So the notch will be usually present at this side. This notch is there. And here from you will start the numbering 1, 2, 3, 4, 5, 6, 7, 8 up till 20. And then you will take a U-turn, and then this is 21 to 40. So this is how you see the numbering of that. Now to begin with, this is the 8085 IC when the top view of that is seen. And this diagram is important because it shows the 40 pins together with their functionality and their directions. So you see that there are various signals which are written here, right? And the directions that you see, it tells you simply that it is either taking data or it is giving data, right? And some arrows are bidirectional, means it can take and give data both. You can also see that some of the signals have a bar over them, so these are active low pins, right? So they have got bar over them, and this terminology must be clear to you from your digital logic course. So whichever version of 8085 you are using, here we are using a variant. There may be many other variants after this, like in the case of Intel i3, you get this first generation, second generation, and so on and so forth. We now have up to 10th generation. So earlier, this terminology was 8085A, 8085B, and so on, right? So now let us begin talking about this IC. So whenever you see a digital component or an electronic component, right, the first thing that you will ask is on what voltage will it operate? So this 8085 AIC, it operates on plus 5 volts. So it is operable on a single battery of plus 5 volt, and that plus 5 volt has to be connected to this pin number 40, right? So the second thing that you will ask is, once you have connected the battery, where is the ground? So ground is pin number 20, right? So this ground is pin number 20. So plus 5 volt is the battery that is required at pin number 40, and ground is the pin where you require uh, this grounding of this IC for reference voltage. So after that, is there any other requirement for this IC? Means you have given it voltage, you have given it proper ground, then what else should it need to operate? I mean, if you see the IC of this AND gate or OR gate, you might have seen it in your digital logic course, which contains 4 to 5 gates per circuit. Then those ICs, if you provide them power, they start to operate. But with microprocessor, the condition is different, because we said that microprocessor, it operates on a certain clock. So for applying that clock also, until unless you apply that clock, this microprocessor will not work, because microprocessor, it works in synchronization with that clock. So you have another input which you need to take care of in order to start this IC, and those pins are X1 and X2. In between these two pins, you have to connect a crystal oscillator, and that crystal oscillator should have a frequency of, it should have a frequency twice as compared to the frequency at which you want to operate this particular microprocessor. Now usually this microprocessor, it operates on 3 megahertz. Usually this microprocessor will operate on 3 megahertz, but if you see the specification sheet, the minimum frequency over which it can operate is 500 kilohertz, and the maximum frequency is 3.125 megahertz, or approximately 3 megahertz, right? So the minimum frequency is 500 kilohertz and the maximum frequency is 3.125, that is 3 megahertz, right? So we would like the microprocessor to operate at its best possible frequency, which happens to be 3 megahertz. Because what's the point of having a microprocessor which can operate at 3 megahertz and you are making it to operate at 1 megahertz? So there is no point. So ideally speaking, we would like this microprocessor to work at 3 megahertz, and for that to become practical, you have to apply a crystal oscillator of 6 megahertz between pin number 1 and pin number 2. Now, why do you need to apply a 6 megahertz IC? This IC is built that way. You have to supply a twice the frequency that you want to have for your microprocessor to operate. Right now, what will it? Why the frequency is halved when it goes into the microprocessor? So the frequency is halved by using a toggle flip-flop, because you will see one more pin, that is your clock output at pin number. I think this is pin number 37. This is the fourth pin. Sorry, pin number, yeah, 37 is this pin. So this clock output is there. You can see that this is output. So from one side you are providing a input to this clock, which is 6 megahertz. 3 megahertz is used by microprocessor and 3 megahertz is made as output from this pin number 37. And why is it so? Because it so happens that if you are having a microprocessor, you and if you interface some external device to it, and if it requires a clock to operate, then this is the source from which it can take that particular clock, right? So for synchronization, this is being done. So half of the frequency is actually passed out to the external device. So this is one of the reasons. Now, one more important point that I want to highlight here is, when you if you see in the current mobile phones, in the current day mobile phones, you might have seen that you have got Qualcomm processor, which can operate at some frequency, but usually it is clocked at a lower frequency than the frequency which on which it can operate up to its maximum extent. Why is it done? Because in mobile, what people usually do is either they play games which require a very high-end graphics card, and it heats up your device. So when your device gets heated up, the processor will automatically reduce its operating frequency, right? And if the operating frequency is already set to its highest, then the processor is actually doing a lot of work. So the processor will get heated up easily. So for the current day ICs, it's a good practice to keep the operating frequency lower than the maximum frequency. But when this 8085 microprocessor was designed, we would like to operate this microprocessor at its best frequency, which is around 3 megahertz. So we apply a 6 megahertz frequency in between pin number 1 and 2, half of which is used by microprocessor and half of which is available at this clock output, which is used for interfacing the peripherals. So with this, your microprocessor IC will start to operate. At least it will come to life. At least it will be in the mode of operating. You have supplied the voltage, you have given the ground, and this is the point where you have applied your um, this thing, clock or the crystal oscillator. Now suppose you want to reset your microprocessor. I mean, if you have a computer, it might be the case that you would like to reset your computer, you would like to start everything afresh. Then for that you have this reset in pin, and mind you, this is a active low pin. So this reset in pin is actually a active low pin. So you have to supply a 0 at pin number 36 to be able to reset this microprocessor. And what does resetting in 8085 means? We have already talked about it. The resetting will mean that this microprocessor will start executing the program from its beginning location. So theoretically, it is 0000H, that is 0000 in hexadecimal. But for the 8085 software that we have seen, it is 4200H by default. So it starts, means whatever programs are written into the external memory are written from 4200H. So therefrom, its program will start executing. So that's what we mean by resetting your microprocessor. So this is the reset input pin, which is the active low pin. So you have to actually give a value of 0 here, 0 volt here, to be able to reset this microprocessor. Now, interestingly, you also see a reset out pin at pin number 3 here. What is the purpose of reset out pin? The purpose is again the same. If you try to interface a externally interface device or something, and if somebody resets the microprocessor, so that output device should also know that the microprocessor has been reset. So if earlier this microprocessor and that device were doing some work, so the output device should know that the microprocessor has been reset by some person, and now whatever task I'm doing is actually not getting done. So I have to start it from the beginning. So whatever its sub modules are, according to that, it will start its task again, right? And the second usage of this is with this microprocessor being reset, if there is a button of reset available in the external device, that reset output will also reset it. So this is about starting and stopping your microprocessor. Once power supply has been done, clock is being applied. If you want to reset or restart your microprocessor, reset in pin is there. Reset output pin will perform the function of resetting every other device that is connected to this microprocessor if it needs a reset, or the devices will know that the microprocessor has been reset. So whatever is their internal mechanism, they will again give their task to this microprocessor for doing, right? Now, let's now talk about interfacing of memory, because once your microprocessor comes to life by applying a battery, by applying a clock and resetting it, now the next task is that this microprocessor would love to perform something. And for performance, it needs a program. Program, as we know, it is a permutation. It's a clever permutation or a logical permutation and combination of the 246 patterns which are made out of the 74 opcodes that are available in 8085 programming language or the assembly programming language. So the next task this microprocessor would like to do is perform some program. And for performing some program, we know that microprocessor does not store program in itself. It needs an externally interfaced memory, and the maximum size of that externally interfaced memory is 64 kilobytes. We have discussed a lot about this. So now we need to interface a memory to it. And we know that 64 kilobytes is the maximum size. It could, the memory that you are interfacing could be lower than that or higher than that. There is no problem. But assuming that we are having a 64 kilobyte memory chip, we are trying to interface it with this microprocessor. Now, that 64 kilobyte memory should have uh, every location which is of 8 bits. You cannot have a 64 kilobyte memory which in which every location is of 16 bits or 32 bits. No, you have to have a 64 kilobytes memory where every location is of 8 bits, because that is the kind of memory this 8085 processor is expecting. And where is it connected? Where is it connected? So that has to be connected because it's a memory. So that memory has to be connected. I mean, you have got these address lines here. You can see that if you see here, this is AD0, AD1, AD2, AD3, etc. till AD7. So these are a combination of 8 bits, right? 0 to 7. So these are used as multiplexed address and data line. We have talked about it. I mean, if you see this AD0 to AD7, this is just one combination. And then from A8 to A15, this is the other byte combination. I mean, if you talk about the address line, they start from this AD0 and end at A15. A total of 16 address lines are there. And If we talk about data lines, it is from AD0 to AD7 only. That is a total of 8 bits are here, right? So if you want to interface an external memory, that external memory should have access to its data bus, and the data bus will be connected through this AD0 to AD7 pin, and it should also have an access to its address bus. So this address bus is connected from AD0 to this complete AD15. So this external memory will be interfaced to this microprocessor through this particular module. If you want to interface directly that memory, these pins can be used there. Right now, here, if the external memory is interface, you know that if you will write a program, it will be fetched inside the instruction register. It will be given to the instruction decoding unit and timing and control unit, and everything will start to execute. But now there is a problem. Since these lines AD0 to AD7 are multiplexed. I mean, sometimes on these lines there will be address, and sometimes on these lines there will be data. But for the rest of the lines A8 to A15, there will always be address. Never the data will never appear. That is why you see that there are the direction is only outwards. However, for this AD0 to AD7, the direction is bidirectional because it can transfer data for which you can either read data or write data. So both bidirectional thing is needed. But for address, it will only transfer the data outside the microprocessor because this microprocessor, if it wants to read memory, it will pass its address through these address lines, which start from AD0 to AD15 to the externally interfaced memory. And once the address is passed there, it will try to read the data. So it needs to take back the data through these lines. Now, there is a problem. How does the external device know that at what time the address is available on lines AD0 to AD7? Because anyway, on A8 to A15, always address will be available. But on the lines AD0 to AD7, at what time is address available and at what time the data is available? So to clear that confusion, we have a address latch enable ALE address latch enable signal here, right? So what happens is, think it in this logical way. Think it in this logical way. This address latch enable signal is you see, if you're trying to read something from the memory, the first thing that you will do is you will provide the memory address on these complete set of address lines starting from AD0 to A15. So you will provide the address on these particular lines, right? Once the address has been provided, now there is no use of that address. So then you would like the externally interface memory to transfer some data to the microprocessor, and that will be obviously done through AD0 to AD7 because the every location in memory is also of 8 bits, right? So that will be done. So this is the logical sequence. In the beginning of the operation, you will be transferring only address, and once the address has been transferred, you will be most of the times transferring your data from the memory, right? To the memory or from the memory. Now, so keeping that in mind, what happens is once this 8085 transfers address over these lines, this ALE address latch enable is made high. What it signifies to the external world is that whatever you see on the lines AD0 to AD7 is address now. It's not data. Because anyway, whether this is ALE is enabled or disabled, the contents on A8 to A15 will always be address. But if ALE is enabled, that will signify that AD0 to AD7 is having address. The lower byte of the address and the higher byte of the address is present here. But if ALE is disabled, it simply means the higher byte of the address is anyway available here, but the lower byte of the address has now gone, and what is now available on AD0 to AD7 is your data portion. So you can take data from there. But now you may ask a question that you might require the same address somewhere else. You might require the same address that you begin with somewhere else. So for that purpose, this address latch enable is externally interfaced with a latch register which will latch your address, that complete address there. Once the address appears on this lines AD0 to AD15 to begin with, if this address latch enable signal is made high, your address will be latched, means this address will be stored somewhere so that when the next thing is getting executed, if the data is present over these lines, you can retrieve that complete address, that 8-bit address from that stored latch, right? From that stored latch. So we will discuss more about this. We will discuss the circuit of this in this current lecture also. So now, after having this memory interfaced with the external microprocessor, we already know that how to decode the address and how to decode the data there. So that thing is already clear to us. How about interfacing? How about interfacing some serial device? Now, you see that memory is a parallel device. It can parallelly transfer 8 bits of data. It can receive or send 8 bits of data to or from microprocessor. But how about interfacing some devices which work in sequential manner? So for sequential data transfer, we have these two pins, serial input data and serial output data. So these two pins, pin number 4 and 5, are actually used for that. So you might have parallel devices which can be interfaced to these lines for address and data. And if you have a serial input, serial output device, so these signals are used to signify that, and we will see a mechanism of how the data is transferred in the case of serial input and serial output device data through sim and rim instructions later when we will do the appropriate programming, right? So this is for that. Now, if the device is externally interfaced to the microprocessor, it's not that it is always allowed to talk to the microprocessor. It's like if the professor is teaching in the class, every student is reading whatever he is teaching. But it does not mean that every student can interrupt every time, or they can simultaneously talk with the professor at the same time. So for that, if a student wants to raise some doubt, this facility of interrupting this microprocessor is provided. So the pins that you see here, the pins that you see here from trap to INTA bar, these all pins are interrupt pins. Means these pins will give the externally interfaced device a way to gain the attention of microprocessor and get his task done. For example, if a professor is teaching in class, if a student wants to ask some doubt, he will raise his hand, so the professor will know that this student wants to ask some doubt. But if the professor is in middle of some sentence, he won't stop there. He will complete that sentence, and then he will say yes, now you can ask your question. So same happens here. Um, if you see this intr pin and intr acknowledge, it is doing the same task, right? So interrupt is provided through this intr pin, and this int a bar pin will let the user know that now this processor has accepted your interrupt. So once you provide interrupt here to int a bar, that interrupt is acknowledged. We will talk more about how to make programs for this particular scenario when we will study the topic of interrupts in the very next lecture. Now, similar in the similar fashion, trap, reset 7.5, 6.5, and 5.5, they are all uh, pins which will take inputs as interrupts. And some of these interrupts are unavoidable, means if that interrupt comes, whatever microprocessor is doing, he has to stop it and serve that request. So that kind of thing can be done by this trap is called as a non-maskable interrupt, means whenever it comes to the microprocessor, whenever that request has been raised, microprocessor cannot neglect it and it simply has to serve that request. So that's what we mean by non-maskable interrupts. We can't put a mask on them and say that you just go, I don't want to serve you. So that's what we mean by non-maskable interrupt. So trap is a non-maskable interrupt, right? But reset 7.5, 6.5, 5.5, INTR, these are all maskable interrupts. Means a device can make a request, but this microprocessor, if it is performing some important task, it will deny that request if it wishes to do so. So trap is usually used for the conditions where there is a means there is a very significant event. For example, if there is fire in the system, there is a mechanism through which the trap request will be made and the system will be reset or something like that will happen, right? So trap is a non-maskable interrupt. It is mainly used for emergency purposes. However, every other interrupt is a maskable interrupt, and depending upon the status of microprocessor, the status of work of the microprocessor, it can be served or not served, right? So apart from this, these interrupts can also be categorized like this. Some of the interrupts are vectored interrupts and some of the interrupts are non-vectored interrupts. What do we mean by vectored interrupts? If you raise a trap request or reset 7.5, 6.5 or 5.5 request, these requests will uh, tell the microprocessor that stop your current work and go to a predefined location, and from there you start executing the code which is already written there. So that's what we mean by vectored interrupts. Vectored interrupts, they have a predefined address at which location that code for execution is written. That code may be changed by the user, but the location at which that code is written is predefined by the user. So trap, reset 7.5, 6.5, and 5.5, they fall in that category. They simply mean that it's a vectored interrupt. However, INTR is not a vectored interrupt. It's a non-vectored interrupt. It does not have a predefined address. The user has to give that address. So we will see that when we will do our programming task, right? So I think, yeah, so this interrupt portion, interrupt pins have been covered. And now the only pins that are left are the control pins, right? So you can see this hold and hold acknowledge. Hold and HLDA means hold acknowledge. What is the purpose of these two pins? So suppose if you have a microprocessor in current age, suppose imagine you have a Pentium 4 microprocessor. It's now a pretty old microprocessor, and you have a pen drive which is a pen drive which you have recently purchased. So obviously it will be faster as compared to the pen drives which were available at that time. So if a faster device is connected to our processor and that faster device wants to transfer its data from the memory or to the memory, which is externally interfaced to this microprocessor, then what will happen is if the microprocessor will do that task, we know that its clock frequency is limited, which is 3 megahertz. So it will be able to do the work at 3 megahertz only. But if you want, since the externally interfaced device is faster than that, so you want the data to be transferred in a faster way. So for that, it will make a hold request. What will happen after making a hold request? The microprocessor, if it accepts this hold request, then it will grant the control of its internal data bus, its internal address bus, and its control signals to this particular externally interfaced device, and the microprocessor will be bypassed for that time. So it will give the control of its internal data bus, internal address bus, as well as the control signals to that externally interfaced device, and a direct access to the memory that is connected. So now the data will be transferred between the device which is externally connected and between the memory directly by not using the internal registers of microprocessor. So microprocessor will have no role to play in that, and the data will be transferred at a better speed, at the speed at which the peripheral is working. So that is the meaning of this hold and hold acknowledge pin, and it is also considered as a control pin, right? Now this input output flash memory bar. This pin is used to indicate whether your microprocessor is operating with the externally interfaced memory or with the externally interfaced input output device. That is, whether it can have a keyboard or some sort of input device, or it can have a monitor. So input output devices are also there, memory is also there. And mind you, all of the input output devices and memory devices have to be connected from AD0 to AD15. So it's not that if you have connected memory to this, all of these signals are blocked. No, you can have a multiplexer and contain and collect and connect multiple devices from this AD0 to AD15, right? So to be able to tell which device is being used, so you have got this input output or memory bar operation, and if the value of this is 1, we are dealing with input output device, and if the value of this is 0, we are dealing with a externally interfaced memory, right? So that is the case here. Then now you have got read and write pins. So you already know that if a externally interfaced memory is there, then what do we want to do? Do we want to read or do we want to write a particular thing? So for that purpose, we are using this read and write signals. And mind you, these read and write signals are actually active low signals. So whenever you make the corresponding inputs 0, they will be activated, right? And Then left are these two signals, S0 and S1. These S0 and S1 are your status signals. They will simply tell you that what is the status. I mean, whether we are writing or reading the memory, or whether we are writing or reading the input output. So this status will become more clear to you when I will show you the tables that we want to see next. So this is the complete IC diagram. This is the complete IC pin diagram of your 8085 microprocessor. And next, what I'm going to show you is the functional pin diagram. So the thing that you see on the right here is functional pin diagram. First one was IC diagram, and the second one is functional pin diagram. So you see here, these pins that you see here, they have been logically grouped here, right? So X1 and X2, that is crystal oscillator, is connected between pin number 1 and 2. For voltage, you have got pin number 40. For ground, you have got pin number 20, right? So these are the basic things that you will require for a microprocessor to come to life. So they are being shown grouped here. Then you can see that there is multiplexed address and data bus from AD0 to AD7, and higher order address bus from A8 to A15, means pin number 21 to 28. So they have been grouped like this. This is a bidirectional because it can have data as well as address, and data requires either reading or writing to and from. So it's a bidirectional bus, and however, this is a single directional thing, right? And for serial communication, SID and SOD are there. For interrupts, you have got these trap, reset 7.5, 6.5, 5.5, and INTR. For your externally interface device, if they want to get the control of your microprocessor, then you have this ready pin, hold pin, reset input pin. And for acknowledging things, you have got interrupt acknowledge and HLDA for this whole thing. So these are also grouped for acknowledgement. And you have got this control and status signals. So address latch enables status bits and input output read write memory. So that is all what we call as control and status signals. And for reset out and clock output, you have got these two pins. So you can prefer to use any of these diagrams. The thing is, you should be able to know what every pin does. And I would like to tell you that if you remember the diagram in both the forms, it is helpful because when you will go to the laboratory, you will have an IC of 8085 microprocessor. And when you perform practicals, uh, in your examinations, you do not have an access to this very nice kind of representation. You have to remember what pin will perform what function. So accordingly, you will be able to design your circuit. So remembering the diagram in both forms is advisable, right? So now let us now come to this status bits S0 and S1. So what do they mean, right? So the status bits, they are single bits and they can have a value of 00, 01, 10, or 11, right? So if the status bits both are 1, it means we are doing a opcode fetch. What do we mean by opcode fetch? Opcode fetch is an operation in which from the externally interfaced memory, we are trying to transfer 1 byte of its code from that memory into the instruction register, which is internal to the microprocessor. So that state is called as opcode fetch state. So if this S0 and S1 is 1 1, it means opcode fetch state. And if it is 1 and 0, then it means that we are reading something. Whatever we are reading, we do not know. It could be a input output device or it could be a memory device. So if S1 is 1 and S0 is 0, it's a read operation. If it is otherwise, that means S1 is 0 and S0 is 1, it is a write operation. And if both of them are 0, that means we are in a halt state. We have stopped our computer. So this is the meaning of these status bit. The status bits that we have seen here, this is S1 and S0. Now you might ask a question that in the pin diagram itself, they would have attached this S1 and S0 near each other. So why have they made this difference? Now this all comes from the fabrication technology. I mean, whatever is the combination feasible to make the area as small as possible and avoid heat dissipation to larger extent. So accordingly, these pins have been designed. So I mean that's why these pins are far away from each other. So it all depends upon the internal transistor construction. Yeah, and one more important point to tell you is that it's a transistor logic (TTL) logic circuit. So this 8085 works on TTL logic, and I'm sure that you must be aware of what TTL logic is because you have read that in your basic electronics courses, right? So it's a TTL logic circuit. It operates on 3 megahertz, and for that, a 6 megahertz crystal oscillator is needed at pin number X1 and X2, and it works on 5 voltage ground. Now, after this, this is a elaborate status of your control signals. The control signals that you see here, that is this address latch enable S0, S1, input output memory, read and write. So this is an elaborate table for that, right? So here what happens is, if you see that we have already talked about S0, S1 being 00, 01, 10 or 11. Now if you interface them with I0 and M signal, if you combine this with I0 and M signal, then you can simply see that for memory write operation, obviously this is, oh sorry, this is M bar. This is not M. This is IO slash M bar. So this is not typed properly because IO slash M bar is the signal that we have seen here. I mean this pin IO slash M bar. So this is that particular signal. So please read it that way. So now if you want to write something into memory, this M bar should be equal to 0. So that is why this bit is 0. Similarly, S1 should be 0 and S0 should be 1. Then only we can perform the write operation. So you can see here for write operation, the status of S1 should be 0 and S0 should be 1. So S1 is 0 and S0 is 1. That's why we are able to perform write operation. But which write operation? Because this memory bar is 0, so we are performing the memory write operation. And the write control signal WR bar will be equal to 0 because it's an active low signal. So that is the active low signal. So you can see here that there is this signal write bar. So this is an active low signal. So depending upon S0, S1 and this, the status of this write bar signal will be decided. So you will get write bar is equal to 0 there. Similarly, you can see that for memory read, what is the status of bit opcode fetch? So opcode fetch, you have to do it from memory itself, right? Because opcodes are usually written in memory. So you have to do it from memory itself. And that is why there is nothing called as opcode fetch from an input output device. So that is done from memory only. Now, for input output write read etc, you have got same options. Then now these are important, these last four are important. uh, if everything is one, so you have a interrupt acknowledge cycle. INTA bar will be equal to 0 there. So what is this INTA bar? You have seen this INTA bar at this particular pin number 11, right? In this elaborate diagram, this INTA bar is the interrupt acknowledge for interrupt request, which is made externally by some device. So that's what is necessary here, right? So after that, you have got hold. For hold, S0, S1 will be 0, and input output slash memory bar signal will be tri-stated, means it is in a high impedance state. So in binary logic, there are two states, 0 or 1. But then if you do not want to use these two states, then there is a high impedance state. You are already aware of that, I guess, from your digital logic course. So that high impedance state is represented by this Z symbol, right? So this is the status for hold, and in that case, your read and write will be in high impedance state. This means that they will not be read as 0 or 1. There will be a high impedance state. Similarly, for halt operation, we do not care. This excess means don't care. So S0, S1, they do not matter. Only this input output slash memory bar is in high impedance state. And similarly, for reset operation, you have got the same thing. You have got the same thing for that. So this is the elaborate status of the control signals that you have got here, right? Now, INTR usually works in this way. If there is a peripheral which is attached to your microprocessor and your microprocessor is there, this peripheral will make a request to this INTR pin and the microprocessor will acknowledge it through INTA pin. So this is a very simple diagram to explain the INTR and INTA A bar pin. But you know that you know how to what should be the status of these S1, S0 and I0 slash M bar from this particular table. Now, coming to this latching part of the address, I mean, I told you that this AD0 to AD7 is a multiplexed address and data bus. After that, AD8 to AD15 will always be address. But if you want to have address and data separately, what we will do is on this AD0 to AD7, you will connect an IC 74373 latch. What will this do? And you will also connect this address latch enable signal here. So whenever address latch enable signal is on, it will simply mean that whatever you see on this AD0 to AD7 pin is your address. So whenever this is on, this IC will become on. And whenever this IC is on, these AD0 to AD7 are connected to this IC2. So that state will be kept in this memory. This functions like a memory, and that state will be kept here, right? So this address A0 to A7 will be available there. And that same AD0 to AD7 has been connected to this line. But since this ALE is 1, whatever appears on this line will not be read. It will not be read because we know that when the address latch enable is 1, the only sensible information that we can get is the address from those particular lines. Same address will be available here, but we won't be reading any address through this particular line. When this address latch enable becomes 0, in that case, whatever is available on this is data. So we do not want the stored address to go because anyway, A8 to A15 they contain the higher byte of the address, but the lower byte of the address has been trapped in this. So whenever the next clock cycle comes, this ALE becomes 0, so that this latch is disabled, and only we can read data from that. We cannot write anything into it. So now whatever is put on this particular bus is actually the data. So we will be reading the data through this part. That data will not be actually able to be stored in this because this ALE will become 0 in that particular case. So that's how this address is latched. Now you will ask a very natural question: what is this IC? How is this address latched? So any guesses? I guess for storing data, you already have D flip-flops. So this is the complete internal structure. You have got a simple D flip-flop for every input to output combination, and this address latch enable is attached to that D flip-flop. So whenever that address is available here, this ALE will activate that particular D flip-flop. So there will be 8 such D flip-flops, and they will all store the same data. And when this ALE will become 0, that state will be retained as long as you want it to be there, right? And apart from that, there are these 8 lines which can be treated as data line when this ALE is 0. So this is how the address latching actually happens. And these devices should be externally interfaced to our microprocessor. So this device should be externally interfaced. This is what we need to do. This is what we need to do externally to the microprocessor. Because if you see the actual diagram of microprocessor, it has only got these address lines and data lines multiplexed and these address lines. So if you want to read address separately even after it is gone because of ALE becoming 0, so you have to make this external arrangement. So this 7437 is an externally interfaced integrated circuit. So microprocessor as such is only the brain. If you want to do any sensible operation, you have to apply some externally interfaced devices there. Now out of these control signals also, you might have seen these pins: input output slash memory bar, read and write. Now this externally interfaced 3 to 8 decoder is also used to be able to convert these signals into input output write, input output read, memory write and memory read signal. Because if the input output signal is, if this particular signal is high, we already know that we are going to deal with the externally interfaced input output device. And if the read signal is high, we will know that in that input output device we are going to read some data from that. So to make the things more easy, we have used this 3 to 8 decoder, out of which we have applied this input output read and write signal to the 3 inputs, and we have got this 8 outputs here. And the sensible outputs in which we are interested are input output write, input output read, memory write, and memory read. Because if any of these signals is high, an appropriate operation could be initialized. So we do not need to look at 3 signals now. After applying this decoder, since in decoder any one of the outputs can be high, or if it is an active low device, it can be activated. So if any one of these is on, we can say that if this is on, we will say that we are doing the memory, write operation. If this is on, we will say that we will using input output write operation. So we only have to monitor just one active signal out of this output instead of monitoring these three signals simultaneously. So this decoder is also of a great help, and this is 74138 decoder, which is a very usual 3 to 8 decoders that you see in your laboratory. So this is also externally interfaced to microprocessor to make things more easy. And this table is the table which you have already seen. So this is just a repetition of that, under what circumstances what operation will happen, right? So this is the complete structure which is known to us as of now for a microprocessor. This is your microprocessor, and you have interfaced a latch to it for address latching purposes on AD0 to AD7. So this is AD0. This should have been AD0. It's a misprint here. So it should have been AD0 here, and this latch is used to address the lower byte of the address, complete address that you have got, and this is the data section. And this decoder is used for converting these control signals into these control signals, right? So you do not have to monitor these three signals. Your work will be done in these four. Now, one more question that one can ask is, these left portions which are not used, what is the purpose of these? So they have got no purpose. We are not looking for those outputs, right? So we are only looking for these combinations, but out of these 3 bits we can make 8 combinations, but only 4 combinations make sense, because if you will put this read also as 0, write also as 0, then what will happen? You are reading and writing simultaneously, so that does not correspond to anything. But as per the bigger table that we have seen here, that has got some different interpretation, 0 0, and this z is don't care, so it will be in the state of hold. So if you want to use that for hold signal, you can use it for hold signal, I mean the output of this particular decoder, right? So this is the complete structure that is in our mind now. We have this microprocessor, we have interfaced a latch and a decoder to it for a better performance, right? So there are devices which have to be externally interfaced to microprocessor. And the laboratories, I am going to show you the kit for this microprocessor. So you will see that this microprocessor is there, and there are various ICs of this kinds which are associated with this microprocessor, are connected to this microprocessor for purposes of operation, right? So now at least these two ICs have started to make sense to you in this particular lecture. So in this particular lecture, what we have done is we have just got introduced to the pin diagram of 8085A and the functional pin diagram of 8085A. And we have also seen some externally interfaced integrated circuits. We have also seen some externally interfaced integrated circuits which will make our job easy, right? If this microprocessor is there, you have these externally interfaced ICs which will make your job easy. So that's what completes the description of functional and pin diagram of microprocessor. But anyway, you should read your books for a more elaborate and complete description. I have covered most of the points that are required for us. And as per our plan, in the next lecture, we are going to start with interrupts. So these interrupts will have some programming part also and some theoretical parts also, because in the programming part we haven't covered programs of interrupts. So next lecture is going to be interesting lecture where you will see how a externally interfaced device can interrupt the microprocessor, and in what way the microprocessor is going to serve or not to serve that particular thing, right? So I guess this is it for this particular lecture. And you should always start practicing codes, because programming is also one very important aspect of this assembly language. So practice a lot of codes, and if you have any doubts, you can always reach me through WhatsApp or through any means that are available to you. So thank you very much for watching this video. I will see you in the next video.